Colligative properties of dilute solutions. So what are the colligative properties? The properties of the solutions which depend upon the number of particles of the solute are called colligative properties. So they do not depend on their nature. These are the properties of solution, not the pure substances. Here we need to make this point in consideration that the properties are actually for solutions, not for solute or solvent as pure substances. So the overall properties of solution are actually different from the components that are pure substances known as solute and solvent. So there are four types of colligative properties, including the first one is lowering of vapor pressure. So in this lecture we will discuss the first property, and the others include this, which is the second one is the elevation of boiling point. Third one is depression of freezing point, and fourth one is osmotic pressure. So gradually we will discuss these four kind of colligative properties, and let's discuss how these properties are developed. Actually, all the colligative properties are developed due to the lowering of vapor pressure, which we are going to discuss today. So all these properties are obeyed when the following conditions are satisfied. So first one is solution is dilute. This condition is necessary as the solute particles are distributed in a way that they have their own contribution to the overall properties of the solution, as they are far away from each other in the dilute solution. When we use the concentrated solution, the particles of the solute are not in isolated form, and they also interact with each other, so thus they affect the overall properties of the solution. And in this concentrated solution, the number of particles do not affect the overall properties, because these particles are already in concentrated and well connected states. So here when the solute particles are isolated, then they can have their individual contribution to the overall properties of the solution. Second condition is solute is non-volatile. The meaning of non-volatile is that there are stronger forces of interaction between the solute particles, which do not allow the separation or isolation of each particle so easily that they can become the part of the air over the surface of the solution. So it means that all solute particles must stay within the solution, as they are non-volatile, means high boiling solute, and the forces of interaction between solute particles are stronger. So when they are dissolved in the solution, these solute particles are separated by the solvent, and they are making solute solvent interactions in such a way that the solute interaction are neglected, as solute particles are separated and acting as individual particles within the solution or the solvent. The third condition is solute is non-electrolyte. The meaning of non-electrolyte means that this solute cannot conduct the electricity. So now come to the lowering in vapor pressure. So we have already mentioned different statements of the Raoult's law in the previous lectures. So when a non-volatile, non-electrolyte solute is dissolved in volatile solvent, means low boiling liquid, at normal temperature, the solvent particles are evaporated and making the contribution of solvent particles at the surface of the liquid, and the pressure of the solvent at the surface of the liquid is known as its vapor pressure. So then according to the Raoult's law, the relative lowering of vapor pressure is equal to mole fraction of the solute. So we have already defined this definition, that is the relative lowering of vapor pressure means the change in vapor pressure or lowering of vapor pressure with respect to the vapor pressure of the pure solvent, equal to the number of particles in terms of mole fraction. So here del P is lowering of vapor pressure, P naught is vapor pressure of pure solvent, and X2 is the mole fraction of solute. The mole fraction of solute depends upon the number of moles of solute, that is N2, and the total number of moles of solution. So we already have defined the mole fraction, that is for solute. This is denoted as X2 is equal to number of moles of the solute over total number of moles of the solution. So here N1 is the number of moles of solvent, whereas N2 is the number of moles of solute. So by comparing equation number 1 and equation number 2, we can replace the X2 with this factor. So here we have X2 is the mole fraction of the solute, and 2 is the number of moles of the solute, and 1 is the number of moles of the solvent and the number of moles of solute. So here we have equation number 2, and we can replace the value of this factor into equation 1. So we get the relative lowering of vapor pressure, that is equal to, so we get equation number 3. So the number of moles of any substance is the ratio of mass of the substance to its molar mass. So we usually take the mass in gram over molar mass, that is the mole. So for N1, that is the moles, number of moles of the solvent. So here we need to take the weight, that is mass in gram of the solvent over molar mass. And similarly for the solute, here we have weight of the solute in grams over molar mass. So W1 and W2 are the masses of the solvent and the solute respectively in the solution, and M1 and M2 are their molar masses. So we can replace the value of N1 and N2 from these two relations. So we get the equation number 3 as change in pressure with respect to the vapor pressure of the pure solvent, or it is also known as relative lowering of vapor pressure, that is equal to the which is explained in terms of masses and molar masses for mole fraction of the solute. So here we need to consider a thing that equation 4 can be simplified by considering that the solution is very dilute, hence N2 can be ignored in the denominator. So the W2 over M2, this term is considered to be negligible. We can see from an example that for example, if we dissolve 0.01 gram of sodium chloride to 1 liter of water, that is a kind of dilute solution. So the number of moles of sodium chloride will be 0.01 over its molar mass, that is 58.5. It will be equal to, so this ratio is extremely small when it is contributed in denominator. So we get the modified equation number 4 as relative lowering of vapor pressure, that is equal to W2 over M2 over the ratio of the W1 over M1. So we can rearrange this equation as equation 5. So with the help of this equation, that is equation 5, we can calculate the molar mass, that is M2 of the solute, which is non-volatile non-electrolyte. So here we are going to discuss the lowering of vapor pressure as a colligative property. In order to have an understanding of this fact, let's consider 3 solutions having 6 gram of urea, 18 gram of glucose and 34.2 gram of sucrose in 1000 gram of water in separate vessels. So here we have 3 vessels containing urea, that is 6 gram, glucose is 18 gram and sucrose, that is 34.2 gram, each containing 1000 gram of water. As these solutes are non-volatile and non-electrolyte, from the given quantities, it is clear that all these 3 solutions are 0.1 molar each. As we have taken the 1 decimeter cube of water, that is equivalent to the 1 liter of water, because the density of water is nearly 1, so the mass, and that is 1000 gram, will be equal to the 1 liter solution. Here we actually taken the water as 1 kilogram. So the molality is actually number of moles over mass of solvent in kilogram. So here we can calculate the moles of urea, glucose and sucrose. The molar mass of urea is 60 gram per mole. For glucose it's 180 gram per mole, and for the sucrose is it's 342 gram per mole. So as we have taken 6 gram, the number of moles of the urea will be 0.1. So as the we have used 1 kg of water, so the molarity that actually the molality of the each solution is 0.1 molar. In each solution there are 1/10 of Avogadro's number of particles of solutes. So here the number of particles of a solute is equal to the number of moles into Avogadro number. So here the number of moles are taken to be 0.1. So here it's become the 1/10 of the Avogadro's number of particles of solute. In other words, every solution has 6.02 into 10 to the power 22 particles of solute for urea, glucose and sucrose. So if we measure the relative lowering of vapor pressure for each solute, we will observe the same factor for lowering of vapor pressure. So in other words, the lowering of vapor pressure is independent of the nature of solute and their masses, but depends upon the number of particles of the solute. So there are two methods for the measurement of lowering of vapor pressure, known as static method, and the second one is dynamic method. Static method is also called differential manometric method. It consists of differential manometer having a U tube. So here we have a U-shaped tube which is filled with a liquid of low volatility and having low density. So this liquid is almost non-volatile. So there are two bulbs known as A and B in this apparatus. So the one of the bulb is filled with pure solvent while the other has a solution. So here bulb A have a solution and this one is filled with the solvent. And this apparatus is put in a constant temperature bath. Using this apparatus, the difference in the level of the liquid for the that is actually defined by the vapor pressure of the solvent, and the level of liquid here is defined by the vapor pressure of the solution. So from these points, the difference between this and this point is actually the delta P, which is lowering of vapor pressure. So we can divide this del P with P naught, that is the vapor pressure of the pure solvent, which is usually available in literature. So we can calculate the relative lowering of vapor pressure using this differential manometer that is used for vapor pressure measurement. The second method is known as Walker and Oswald's method. This is the dynamic method. So in this method we have two types of bulbs containing the solution having vapor pressure. So for this these bulbs, the solution have vapor pressure that is P, and for these bulbs the vapor pressure is P naught. So for the determination of lowering of vapor pressure, the dry air is passed through these series of bulbs. When this dry air will pass through the bulb containing the solution, it will get some vapors of the solution, and it will move towards the next bulb, and successively this dry air will be filled up with the vapors of solvent. So when this wet air is passed through the U tubes containing the already weighed amount of anhydrous calcium chloride, which have ability to absorb the vapors from the air and make it completely dry. So the amount of the vapors that are absorbed in the air and then which are absorbed by the calcium chloride, which is anhydrous, in these tubes will increase the weight of the calcium chloride. So initially this weight is equal to the number of particles that are absorbed in the air. So in this method we can set the bulbs and which are weighed accurately before passing air. Then we can determine the loss of vapors from the bulbs containing the solution and the solvent separately. The loss in the mass of the solution W1 is proportional to the P. Initially only the bulbs containing solution will be filled, and they will connect it directly to the U-shaped tubes without connecting to these bulbs which are dipped in the solvent. So the number of particles that are absorbed by the dry air will be equal to the vapor pressure of the solution, or it should say we correctly said that it's directly proportional to the vapor pressure of the solution, that is P. So we can say that at first attempt, when the air is passed through the bulbs containing the solution only, so the weight that is increased for the dry calcium chloride with the absorption of the vapors that have been absorbed from the solution is W1. So W1 is proportional to the vapor pressure of the solution. When this air is passed over the solvent bulbs only, then it take up the vapors of the solvent till it is saturated up to P naught. So this is the vapor pressure of the pure solvent. The additional amount of vapors taken up is proportional to the difference. So so here it is more appropriate that at first attempt only the air is passed through the bulbs containing solution. The vapor pressure of solution will be equal to the or number of particles from the solution have been absorbed in the dry air, and proportional to weight 1. For the second case, the dry air is successively passed over the solvent bulbs. Then it takes up the vapors of the solvent till it is saturated up to P naught. So here this air is actually the air that is coming from the this complete connection. For first case we have absorbed the air that is coming from only the solution. For this case W1 is proportional to the vapor pressure of the solution. Here W1 is the increase in weight of this anhydrous calcium chloride which have absorbed the solvent from the dry air which is coming from solution only. For the second case we have a W2, that is the weight of the bulb containing the calcium chloride which have absorbed the vapors from the air which have been passed through the solution as well as solvent bulbs. So for this case the additional amount of vapors taken up to is proportional to the difference, that is P naught minus P. So the W2 will be proportional to P naught minus P, and as this is proportional to W2, so we can add this and this equation together, so we get the relation given here. So overall we have a proportion, that is the P naught, that is proportional to the W1 plus W2. So now divide the equation 1 with equation 2. So we get the lowering of vapor pressure over the vapor pressure of the pure solvent, that is equal to W2 over W1 plus W2. So here we have a relative lowering of vapor pressure, that is equal to loss in the weight of solvent pulps, and over the total loss in the weight of solution and the solvent. So from the value of del P over P naught, we can calculate the mass of the solute, that is the molar mass.